Okay, so we're going to be looking at module 1, which is properties and structure of matter. Now, in chemistry, matter is a very simple like wording. If we refer to anything as matter, it means anything of mass. So anything that has mass is a form of matter. Okay. In this module, we're going to be looking at things like electronegativity, ionic covalent nature of bonds, but we're also looking at things called ionic networks, covalent networks, and stuff like that. Okay, so this is what we're going to try and look through first, is the different types of bonding in some kind of chemical compound. Okay, so we're going to be looking through this. Let's just quickly go over two wording. So we have a thing called intra and intermolecular bonds. So intra is the bonds between atoms, and then inter is bonds between molecules. So between molecules or between atoms. Okay, so intra between atoms, inter between molecules. And we'll look at how each of these affect the molecule. Okay. So firstly, types of intra bonds you can see is metallic bonds, ionic bonds, and covalent bonds. So we'll quickly go through these because these are some of the stuff we did cover last lesson. Okay. So if you have a look at your periodic table, there's 4 main types of metals. There's the alkali metals that will be in group 1 of your periodic table. There is alkaline earth metals, that's in group 2. You'll have rare earth metals, and you'll have transition metals. Now, when metals combine together, if you ever see, they come as a solid and they're very jam-packed together. So how is that the case? That's to do with the metallic bonding model. So if you think about it, think of a metal being a positive cation. So these ions here, these are the metal atoms or the metal nucleus. Okay. And it kind of constructs itself like a 3-dimensional cube. So it's a 3-dimensional lattice. This is what we mean by a lattice. You can see that there are these black dots here, or these dark dots here. Okay. Now, according to this metallic bonding model, a piece of metal is held together because its positive atom, so the positive atom in the metal, is surrounded by a series of free moving electrons. In chemistry, we call these delocalized electrons. These electrons are moving past these positive cations. If you remember from our understanding of forces, if you have a positive charge and a negative charge together, they will try and attract towards each other. So that's kind of the reason why metals are held together in a giant packed lattice or big solid, because the negative electrons and the positive cations of the metal try and get more attracted towards each other. Another thing is when it comes to electricity, if electrons are free moving, so they are delocalized, you get conduction of electricity. So that's very useful too. And so with metals, the reason why they're held together is because of this electrostatic attraction between negative electrons and the cations in the metal's nucleus. Okay, so let's just look at looking at the properties of metals. So a metal has a hard, it's hard. It has a high boiling point and melting point. The reason being is because of a strong electrostatic force. So it holds the substance together. So the reason why metals boil and melt at a really high temperature is because it takes a lot of energy to separate these atoms away from each other. Okay, so it takes a lot of effort to move these atoms away from each other. Now, metals are good conductors. Like I said before, that's because the electrons are free to move. If you put some kind of electric cord through it or some kind of electric field, the electrons will try and migrate towards a particular direction. That's where you get an electric current. Metals are malleable and ductile. The reason being is because these strong electrostatic forces ensure that there is no breakage. So the reason why you can bend metal is simply based on the fact that it's not brittle. The positive cations can be just kind of shifted around. Other things we know about metals is it's lustrous, so it's very shiny. We also know that metals do lose some electrons in chemical reactions because it's easy to remove. So it's kind of like that. Some limitations with talking about the metallic bonding model, it's just that we can't really explain exactly why there is a range of boiling points. So if you have a look at this periodic table here, there is a huge range of different boiling points of all these transition earth metals. So we can't really explain with this model alone why that's the case. And also we can't really explain why some metals are magnetic and some metals are not. But that's not really what we're looking at here. We're just trying to look at the bonding. Next one we have is ionic bonds. Now, ionic bonds is very simple. It's a bond between a metal and a non-metal. So you have sodium here. That's the metal. And then we have the chloride atom, which is the non-metal. Okay. Now, sodium is going to donate or give its valence electron to chlorine. So the metal will always donate its electron. Okay, it will always donate its electron towards the non-metal. So if you think of it, the metal acts as a giver of electrons, the non-metal acts as a receiver of electrons. And so we get this here. So if you have a look here, sodium has a positive charge. That makes the sodium ion a cation because it's positive. Again, that little T in the middle here gives you the sign of positive. And then chlorine or chloride, that's a negative ion, so that is an anion. Okay? And so we have something like this telling it to us. It has a full valence shell. What we mean by a full valence shell, you can see the outer shells here. So two outer shells here, the outer shell here. They're full of electrons. So when it has a full valence shell, the compound is stable. So that's why chemical reactions happen. Because we have high volatility in the chemicals and they want to become stable. If we look at different properties of ionic compounds, let's say a high melting point, okay, because ionic bonds are very strong. You can see again here, this is just an attraction between a positive charge and a negative charge. So it has strong electrostatic forces holding the atoms or the ions together, okay? So it has strong electrostatic forces. I'll write that down. So you have okay, so there's that. Ionic compounds are usually hard and brittle crystals. So strong forces between particles make them difficult. Again, this just relates back to the electrostatic force. Ionic compounds do not conduct electricity in the solid state, as you can see, because the electrons can't move around freely. However, if you ever dissolve it in water or make it into a liquid, it will conduct electricity very well. So there you have that. Okay? Think about it this way. Now, salt is an example of an ionic compound. If you dissolve the salt into water, okay, that frees up the positive and negative ions in the solution. So using salt as an example, which is basically sodium chloride. When sodium chloride goes into solution, you have positive sodium ions, you have negative chloride ions. You'll have a sea of them. Now, because you have these negative and positive charges, they act as a way to induce electricity. And so that's why it works. If you did the same thing for metal, so you melted metal, you'd actually see a decrease in the electric conductivity. So the electric conductivity actually goes down, whereas with ions, it increases. And then you might find a situation where you have a big ionic lattice. Now, this is, if you think about it, just think about it there. Ionic lattice is similar to you looking at a small speck of salt. So what's actually happening? Well, the thing is, most ionic compounds don't come as just a simple compound of two atoms. Generally, what happens is they actually form with other ions of the same type. So we have fluoride bond with sodium and then sodium again with fluoride. These are still all ionic bonds, but they've essentially made a big connecting network, and we call this network the lattice. The overall charge, the net charge, is zero because all the positives and all the negative charges added together equates to zero. These have a much higher boiling point and melting point, just because there are a lot more ionic bonds, so that makes it a lot stronger as a structure. And so trying to spread the atoms apart would be a lot more difficult. Next we have is the ionic crystal lattice. Same thing, it's still a lattice. You have your sodium chloride. So the reason why you see table salt look like a little cube of some sorts is because it takes on this crystal lattice structure. So there's that reason why salts look like that. Okay, so this was a little video here. I'll upload this later so you can watch. And so why do ions exist? So why do ions and compounds exist? Like I said, there's a there's a little rule in chemistry called the octet rule, which essentially says that all atoms want to have a valence electron structure similar to the inert gases. Now, the inert gases are your group 8 um, elements on the periodic table. And basically, all atoms want to have a full outer valence shell. So you can see how lithium here has one valence electron, and fluorine here needs one more electron to get a full outer shell. Now we know that anything in group 1 and anything in group 7 are very reactive elements. So that's why they're reactive, because they need a full outer shell, or they're very close to achieving the full outer shell. When they achieve the full outer electron shell, that's when they become stable overall. And that's why compounds try and congregate together. All right, now how do you determine if something is an ionic bond. Now this goes back to what we did on Wednesday. It's by looking at the electronegativity between two elements. So fluorine has an electronegativity of 4 and potassium has an electronegativity of 0.8. If you subtract the two, that's your electronegativity difference. Let's look at the range that quantifies something as being ionic, something that quantifies it as being covalent. Okay, so electronegativity means how willing is an atom to attract an electron. So fluorine has the highest electronegativity. Out of all the elements of the periodic table, fluorine is the most likely of attracting electrons towards it. Okay, so if we have two elements and we try and look at their difference in electronegativity, and we get a value that's less than 1.5, then we form a covalent bond. Now, a covalent bond, if you recall, is a bond that occurs between two nonmetals. So when two nonmetals come together, okay? We know for a fact that the nonmetals have a higher electronegativity, and so it's always less than the 1.5. If we have a situation where the electronegativity is greater than 2, so it's bigger than 2 here, then it is an ionic bond. You'll see that we now have a range where it's a little range called 1.5 to 2.0. So if we're between those two gaps, what would that tell us? Would it be covalent? Would it be ionic? Simple answer is if there is a metal involved and you get a range of 1.5 to about 2, we still call this an ionic bond. If, for example, it is 1.5 to 2, and we only have nonmetals, then we'll consider that to be a covalent bond. Okay, so that's just a little exception to the rule that we need to take into account. So the last thing we're going to look at is a covalent bond. Like I said, covalent bond is a bond between two non-metals. And this occurs through sharing valence electrons. So by sharing valence electrons, non-metal atoms will form a full outer electron shell. These, out of all the bonds we've talked about, all the intramolecular bonds, these have the lowest strength, so they're the weakest ones. That's why all covalent compounds, relatively speaking, have a low melting point and a low boiling point, just because their bonds are weaker in comparison to ionic bonds. So this is relative to ionic and metallic bonds. So they're weaker compared to those. As you can see in this diagram here, the electrons are kind of locked in. So if it's locked in, then there is no conductivity of electricity. Okay, so covalent compounds do not conduct electricity. Even if you melt it, you boil it, it won't conduct electricity because it's not made up of positive and negative charge particles. It's simply atoms that are sharing electrons with each other. Okay, so let's have a look at the next one. Now, covalent compounds actually do something very similar to ionic compounds. They can actually form covalent lattices, or they can form a lattice structure. Not all covalent compounds can do that, So covalent lattice is a very rare type of covalent substance. Usually you see it with silicon. You also see it with carbon. And what's essentially happening here is imagine you have all these silicon atoms, and what's occurring is it's sharing these electrons around. So you have a silicon atom, electrons are being shared here, 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 but then it's also sharing these electrons to this atom here. And so by sharing these electrons around with each other, you can think of it this way, you could also share back this way. They kind of congregate together and hold each other together. So that's a really unique thing. That's what keeps it very strong um, as a structure. So if you ever look on the periodic table and try and look at the melting point or boiling point of all the elements, you'll find that the transition metals have a really high melting point, but you also find some non-metals also having a very high melting point or boiling point. Now, carbon, okay, we know carbon as soot, we know carbon from carbon dioxide. Carbon actually has a really, really high melting point. As a matter of fact, if you have a look here, it actually has the highest melting point of all elements in the periodic table, based on this periodic table I'm using here. The reason being is because it forms this covalent lattice structure. Okay, so it forms something like this. A covalent network, or a covalent network, covalent lattice, same idea. So don't get them confused. Now, carbon can form a network into a diamond, into graphite. Okay, silicon can make silicon dioxide and all that. Now, the whole purpose of this, it allows you to have a really high melting and boiling point substance. But also we know that diamond is one of the hardest materials on earth. We also know that graphite, not only can you use it to write, but you can use it to conduct electricity and all that. Oh, and also, if you never knew, diamond and graphite are both made out of carbon. So the next time someone gives you, or you try to give someone a shiny piece of rock, you're really just giving them shiny carbon. Okay, so the other thing we have is a covalent molecular compound. Now, a molecular compound lattice. What's the difference? A lattice is just a massive series of covalent bonds. A covalent molecule is basically just a very simple compound between, at most, two atoms. While as a network is with an incredible amount, finite amount of atoms. Okay. So what we have here, electron is being shared. Covalent molecules have a low melting point and boiling point because their intermolecular forces are weak. Okay, or their intramolecular forces are weak. Covalent networks, high melting point, high boiling point. Okay, so there we have that. If we just quickly go through a little thing here, we have so a little thing we have here is comparing graphite and diamonds. Now diamonds you can see here and graphite you can see. There's really only one difference. In diamonds, you have 4 carbons bonding with each other. So you have 4 carbons here. And that extra, and then if you have a look at graphite, it's 3 carbons joined together. And this has a massive implication between the two. Now carbon, or diamond, sorry, because it has 4 carbons bonded to it, makes it extremely hard and makes it really good at cutting and breaking down materials. So that's the advantage of that additional carbon bond. If carbon, or if graphite with 3 carbons, you see something slightly different, okay? Because it has one less carbon, it actually frees up the electrons. So what would happen is you have like this little sheet of carbon on top of each other, and then in between the two layers of carbon, you have electrons moving around in between. So that's why graphite is a good conductor of electricity. Just so happens it allows electrons to move around. This also goes into another concept we'll just quickly talk about, which is allotropes. Okay? Now, graphite and diamond are both made out of carbon. However, they have a different structure to each other. That's what an allotrope is. Basically, the formation of the same element, but it has a different chemical property because it has a different lattice structure. So that's kind of what they are. Okay? And so that's what we talk about when we talk about graphite, diamond, and then a thing called buckyballs. Okay? So just to end it off here, remember intramolecular bonds is the bonds between individual atoms. And we talked about those bonds being ionic. We talked about those being covalent. And we talked about that being metallic. Okay? And we also looked at inter, which is bonds between molecules. So that's where we get the lattice structures. So if we're looking at just simple molecules, that's due to the intramolecular bonds. And if we're looking at the lattice structure or the covalent networks, that's because of the intermolecular bonds. But we'll talk a little bit more about the intermolecular bonds then. Okay? So that's basically what you need to know. What I want you to do is make some notes about this into your books and then complete the questions that I've outlined on Google Classroom. Okay, I'll pause that there. And letting you know this is going to be put onto online, so you can rewatch this lesson when you want to as well.